So simply I am defining here what is electronic configuration. The total distribution, which means distribution in the sense, okay, spreading. So the total spreading or distribution of electrons in the subshells which I mentioned above SPDF is nothing but electronic configuration. An element location in the periodic table reflects the quantum number. Very important point. If you take an element location in the periodic table reflects the quantum number. What it reflects? A quantum number of the last orbital. Now, in this section, we will observe a direct connection between the electronic configuration of the element and long form of the periodic table. Now, electronic configuration in a period, let us take it, periodic table. If you take the periods, okay, it indicates the value of n or principal quantum number for the outermost or valency shell. The outermost shell is nothing but the valency shell. In other words, successive periods in the periodic table is associated with the filling of electrons in the next higher principal energy level. As we have discussed, energy levels are indicated by n. Let us take n equal to 1 first energy level, n equal to 2 second energy level, etc. It can be readily seen that the number of elements in period is twice the number of atomic orbitals available in the energy level that is being filled. As you are aware of it, the first period n equal to 1 start with the filling of lowest level, that is 1s, and therefore has two elements, hydrogen. Let us take a hydrogen. Okay, in this hydrogen 1s shell is there, 1s1. Okay, and helium, let us take 1s2. What about helium? It will have a 1s2 when the first shell potassium is completed. For potassium it is completed. So second period n equal to 2, let us take n equal to 2, starts with lithium. Okay, second energy level in a periodic table, n equal to 2, if it is principal quantum number n equal to 2, it is indicating lithium. And the third electron enters the second orbital. Let us take the third electron. Okay, this third electron going to enter into second s orbital. So this second s orbital definitely it will belongs to next element. So if you take one more example, beryllium has 4 electrons. In this statement you have seen the next element, beryllium, has 4 electrons and has the electronic configuration 1s2. Here I will write the electronic configuration 1s2 and let us take s orbital and 2s2, second s orbital 2s2. Now starting from the next element, boron, if you see, the 2p orbital are filled with electrons. Okay, after s orbital we have a p. So if you take the p orbital in this series, p orbital, 2p orbital, it will be belongs to next element called boron, and orbitals are filled with electrons. So when the L shell is completed at neon with the electronic configuration 2s2 and 2p6. Okay, so when it is 2s2 2p6, this electronic configuration is belongs to another element called neon. Neon is a zero group element. Here onwards, zero group elements are going to enter. Finally, thus there are 8 elements in the second period. If you take the second period, let us take the second period, there are 8 electrons. How many electrons are there in the second period? 8 electrons are there. The third period, if you take the third period, let us take it, n equal to 3 begins with sodium, n equal to 3 begins with sodium, and the added electrons enters into 3s orbital. Successive filling of 3s and after 3s what will be there? 3p. After 3p what will be there? spd. And after 3d what will be there? spdf. Okay, now let us take 3p orbital. When they are gives to the third period of 8 elements. Okay, after 3p orbitals filling the electrons, they gives rise to the third period. Okay, 3p orbital, third period, and third period contain 8 elements. How many elements will be there? 8 elements, starting from sodium to the 0 group element called argon. Now fourth period n, okay, n equal to 4, start at potassium. Okay, let us take potassium, and added electrons fill the 4s orbital here. 4s orbital filled. Now after 4s orbital added electrons, now you may notice that before 4p orbital is filled. Now imagine that already 4s orbitals are filled. Now 4p orbitals are going to be filled, or before filling 4p orbitals what will happen? So that is the question here. Before filling up, okay, 4p orbitals, as you can see, 4p orbitals are filled. Filling up of 3d orbitals, okay, filling up of 3d orbitals becomes energetically or more energetically favorable, and we come across so that 3d transition here generally, or 3d group elements are going to be, or transition of elements, series of elements are going to be formed. This starts from scandium, as you know that. Let us take a scandium. Here in the scandium's atomic number Z equal to 21, which has the electronic configuration 3d, 14 and 4s2. Okay, here I have mentioned 3d, 14 and 3d1, 4s2. Sorry, it is 3d1. It is 3d1 and 4s2. Now 3d orbitals are filled at a zinc. Let us take the zinc. Z equal to 30 with electronic configuration of 3d10 and 4s2. Now the fourth period ends at krypton with the filling of 4p orbitals. Here you can see that 4p orbitals are going to be filled. Finally, altogether we have seen that 18 elements here so far in this fourth period are commonly observed. The fifth period, n equal to 5. As we have seen that n equal to 4 indicates fourth, what we can call fourth period. Now we are going to see fifth period. In fourth period we have seen 18 elements. In fifth period n equal to 5, beginning with rubidium. Let us take rubidium. The rubidium, if you carefully see, it is similar to the fourth period. Why? Because it is the first element after fourth period. Hence, fourth period and contains here 4d transition. So the rubidium generally contains 4d transition. So the characters of some of the characters of rubidium are similar to the fourth group elements. Starting at now, the 4d transition was completed after rubidium. Now the 4d transition series starting at yttrium. What is that? Yttrium. Now if you take the yttrium, Z equal to 39, this periods at xenon. Total together with filling up 5p orbitals, okay, 5p orbitals, this period ends at xenon. Now we have seen what is fifth period. After that, sixth period, n equal to 6. Now contain approximately 32 elements, and successive electrons enters at 6s, 4f, 5d and 6p orbitals. In other words, filling up of 4f orbitals begin with cerium. What is that? Cerium. cerium Z equal to 58 and ends at lutetium, what is that, Z equal to 71 to give 4F inner transition series. Here onwards, inner transition series. Inner means within the transition series, which is called as a lanthanoid series, going to be formed. About lanthanoid elements and their characters we are going to see, and we have seen so far how lanthanoid series is going to be formed. As you can see, once again I will tell you how lanthanoid series will be formed. In the other order, or in the order, filling up of 4f orbital begin with cerium Z equal to 58 atomic number and ends at lutetium Z equal to 71 atomic number to give the 4f inner transition. This inner transition series is nothing but a lanthanoid series. Okay. Now, seventh period, let us take n equal to 7, seventh period, okay, is similar to the sixth period only. Why? Because sixth period with the successive filling up of 7s, 5f and 7p orbitals include most of the man-made radioactive elements. Okay. In the seventh period, as you can see, elements have a radioactivity. So what is that radioactivity, and what are the various elements that are going to be participate in radioactive process that we are going to see in the further classes. This period will end at the element with atomic number 118, which would be belong to the noble gas family. Filling up of 5f orbitals. Whenever electrons are filling in 5f orbitals, after what will happen? Actinium. Okay, let us take actinium. Actinium is going to be formed. Actinium Z equal to 89, which gives the 5F inner transition series known as actinoid series. Now, after actinoid series, 4F, 5F inner transition series of elements, if you carefully observe them, are placed separately in the periodic table, maintain its structure to preserve the principal classification. So, the principal classification is preserved or maintained by the filling up of electrons in the 4f and 5f inner transition series. Okay. Finally, if you carefully see some of the problems related to our concept, how would you justify? Here the question is given, I will underline it, let us say, let us take it, and important for all competitive exams like JEE and etc. How would you justify the presence of 18 elements in the fifth period of the periodic table? Now solution is given here. How would you justify the presence of 18 elements in fifth period? So which means n equal to 5, okay, principal quantum number n equal to 5, and I equal to 0, 1, 2, 3, as you are aware of it. Now the other order in which energy of the available orbitals, here 4d, 5s, 5p, and increasing order will be 5s greater than 4d, 4d greater than 5p. So this is a solution which you have to mention. You got my point? As you are aware of it, the total number of orbitals available are 9. How many orbitals are available? 9 orbitals are available. Maximum number of orbitals. Okay. As we have seen, maximum number of orbitals are 9. Total number. Now what about the maximum number of electrons that are going to fill here? If you take the electrons that can be accommodated is 18 electrons only. Why? Because as you are aware of it, therefore 18 elements are there in the fifth period. Because of this reason, 18 elements are there in the fifth period. As a result of it, 18 electrons are going to be filled in the respective orbitals. Finally, I have a small diagrammatic representation for you. Here we have lithium. Let us observe this symbol. I have taken it from our NCERT textbook. Atomic number is 3. Electronic configuration is 1s2. Okay, as you can see, 1s2 comma 2s1, or it is also can be mentioned as helium, as you know that next coming element in this series is helium, and 2s1. Okay, so the symbol lithium with atomic number 3, and 1s2 2s1, 2 plus 1 3, or it can be mentioned as helium with atomic number 2 and 2s1. Got my point? And atomic number 11, and the next one is sodium. Let us take the sodium. Atomic number is 11. What is that? 11. And electronic configuration will be 1s2, and in the first s orbital 2 electrons are filled, hence it is 1s2. And the next one is 2s2, and the next one is 2p6, and the next one is 3s1. It will be mentioned like this. So count the total number of electrons that are filled in the 1s, 2s, 2p and 3s. In 1s 2 electrons are there. In 2s orbital 2 electrons are there. In 2p orbital 6 electrons are filled. In 3s orbital 1 electron filled. Total 4 plus 6 10, and in 3s orbital 1 electron is there, equal to 11 electronic configuration with the atomic number 11. You got my point? It also can be mentioned as, let us take neon. Next coming element after this series is neon. Okay, and neon plus 3s1. Okay, 3s orbital actually came here. Let us take neon with atomic number 10. So 10 plus 1 11. That also can be mentioned. Next one is potassium. Okay, next one is potassium. Atomic number is 19. Electronic configuration is, in 1s 2 electrons are filled. Okay, so in 2s 2 electrons are filled, and in 2p 6 electrons are filled. Okay, and in 3s let us take 3s, and in 3s 2 electrons are filled. Okay, and in 3p orbital how many electrons are filled here? In 3p orbital 6 electrons are filled, and the next orbital will be 4s1. Okay, count the number of electrons that are filled here in the subshells or orbitals. In 1s 2 electrons are present, are filled. In 2s orbital 2 electrons are filled. In 2p orbital 6 electrons are filled. In 3s orbital 2 electrons are filled. In 3p orbital 6 electrons are filled. In 4s orbital 1 electron is filled. 4 plus 6 10, 10 plus 2 12, 12 plus 6 18, 18 plus 1 19. It is similar to the next series or next period element. So the next period element will be argon. As you know that 4s1 should be mentioned. Okay, the atomic number of argon is 18. 18 plus 1 19. Okay, after potassium one more example I will take, rubidium. So with atomic number 37, and electronic configuration is as followed: 1s2, 2s2, 2p6, as usually they are filling like that, and 3s2, 3p6, okay, and 3d10. After 3d10, and let us take 4s2, okay, and 4p6, and finally 5s1. So now let us count the total number of electrons filled here in each orbital, so that we will get the exact electronic configuration. In 1s 2 electrons are there, in 2s orbital 2 electrons, in 2p orbital 6 electrons are there, in 3s orbital 2 electrons are present, in 3p orbital 6 electrons are there. 4 plus 6 10, 10 plus 2 12, 18, 18 plus 10 28, 30, 36 and 37. So this one also can be mentioned as along with the next series element, that is krypton, and it will be 5s1 automatically reflected here. So which means atomic number of krypton is 36 plus 5s1, which means 37. Total number of total electrons that are filled here. Finally, cesium, let us take Cs. Let us take the cesium with atomic number 55, okay, and electronic configuration here mentioned so far: 1s2, 2s2, 2p6, 3s2, 3p6, 3d10, 4s2, 4p6, 4d10, 5s2, 5p6, 6s1. You can count the total number of electrons. 4 plus 6 10, 10 plus 2 12, 12 plus 6 18, 10, 18 plus 10 28, 30, 36, 36 plus 10 46, and 46 plus 2 48, 48 plus 6 54 plus 1 55. It also can be written as the next series element xenon, and 6s1 will be carried. The atomic number of xenon is 54, and the electronic configuration as per orbitals which contain electrons. Xenon with atomic number 54 plus 1 electron, that is filled in 6s orbital, 55. And finally, you can take one more example that is mentioned there. So far this is electronic configuration of various elements. After that, group wise electronic configuration, so far we have seen elements the same vertical column, groups have the similar valency shell. Now, electronic configuration and types of elements, s, p, d, f blocks. Okay. So before that, we have seen how electronic configuration was there. Electronic configuration and types of elements, SPDF block. Now, the Aufbau principle, whatever we have seen, electronic configuration of atoms provide. Aufbau principle provides the atoms and their electronic configurations. A theoretical foundation of the periodic classification. History, let us learn. The elements in vertical column of the periodic table constitute a group of family. Okay, whatever vertical columns are there in the periodic table, they contain a group of family or elements similar with the chemical behavior. Now, this similar arises because these elements have the same number, same distribution of electrons in their outermost orbitals. We can classify the elements into 4 blocks: S block, P block, D block, F block, depending on the type of atomic orbitals. Now, this is illustrated in figure number 1 that I am going to show to you. Now, strictly helium belongs to S block element, but its positioning in the P block element or P block along with other group 18 elements, so far whatever we have seen, is justified because it has a completely filled valency shell 1s2 and 2s as a result. Exhibit properties, characters of other noble gases. Now we are going to see in the further coming classes. I will detailedly explain what are the characters of noble gases and how they behave. The other exception is hydrogen. It has only one s electron, hence can be placed in group 1. It can be placed in group 1. So the group 1 elements are called as alkali metals. Alkali metals. It can also gain an electron to achieve a noble gas. When alkali metals achieve or gain an electron to convert a noble gas character arrangement, hence it can be behave similar to group 17 halogen family elements. After that, because it is a special case, we shall place, let us take hydrogen separately at the top of the periodic table, and we will briefly discuss the silent features of the 4 types of elements marked in the periodic table. Now, more about these elements strictly, let us take helium. Helium belongs to S block element. It positioning in the P block. What is the reason for positioning it in the P block? Because with other group 18 elements, whatever we have seen so far, justified because it has a completely filled valency shell. Valency shell, you are aware of it. This valency shell filled with 2 electrons. As a result, it exhibits the properties, characters of noble gases. Hence, it is placed in a P block. Okay, except hydrogen gas or hydrogen. It has only one s electron, as you are aware of it. S electron is 1 and hence can be placed in group 1. Alkali metals. It can also gain an electron to achieve a noble gas arrangement. Hence, it can behave similar to group 17 halogen family elements. We have a separate chapter called halogens and their family. There I will discuss with you about briefly halogen family. Because it is a special case, we shall place hydrogen. Let us take the hydrogen. Okay, hydrogen separately at the top of the periodic table, as we have seen so far. We will briefly discuss the silent features of the 4 types of elements marked in the periodic table. I will show the periodic table and marked elements also in the diagram. We will discuss later. During the description their features, certain terminology has been used which has been classified in the section. Now, S block elements, what are their characters? The elements of group 1 alkali metals and group 2 alkaline earth metals, which have NS1 and NS2 outermost electronic configuration, belongs to S block elements. Okay, here clearly I gave the definition for that. They are all reactive metals. They have a character called reactive, and the reaction is super fast, and these metals with low ionization enthalpy. The enthalpy is very much low. Okay, and if you can see, they lost the outermost electrons from S subshell readily to form +1 character, which means ionic character in the case of alkali metals. What about +2 indicates ionic character? In the case of alkaline earth metals, it will be +2. In case of alkali earth metals, it will be +1. That is the difference. What is the difference between alkali and alkali earth metals? We are going to discuss in the further classes. Metallic characters and reactivity increases as we go down the group. These points are very much important because of high reactivity. They are never found pure in nature. Reactivity is more, hence pure form of this compound is not available.